On Monday, January 19, 2026, Earth's magnetic field was struck by an intense and severe solar storm, one that has already been labeled as a record-breaking event. The storm, triggered by a burst of solar particles traveling at incredible speeds, left behind brilliant auroras visible in the United States and across large parts of Europe. As the solar storm unfolded, it captured the imagination of the public, with reports of auroras extending far beyond their usual territories. The geomagnetic storm, in terms of intensity and impact, quickly became a topic of significant discussion among both space weather enthusiasts and scientists. Although the solar storm was intense, it did not come without a level of exaggeration in the media regarding its magnitude. The event marked a breaking of a 23-year-old solar radiation record, which further added to the intrigue surrounding its effects. The geomagnetic storm began its development on January 19th, triggered by a powerful stream of solar radiation, specifically a coronal mass ejection, CME, which hit the Earth's magnetosphere, temporarily disrupting the Earth's magnetic field. This disturbance allowed charged particles to penetrate deeper into the atmosphere, leading to the stunning visual phenomena that so many people witnessed across the Northern Hemisphere. The CME itself had initially been released by the Sun on January 18, 2026, after an X-19 solar flare erupted from a dark, active patch near the Sun's equator. This solar flare was the catalyst for the CME that ultimately struck Earth, initiating the sequence of events that led to one of the most striking geomagnetic storms in recent history. At the time of impact, the geomagnetic storm caused an intense flare of auroral displays. These light shows, also known as auroras, are a direct result of charged solar particles colliding with the Earth's magnetosphere. As the charged particles interact with the gases in Earth's atmosphere, they release energy in the form of light, creating a phenomenon that is both beautiful and scientifically important. The auroras associated with this storm were especially vibrant and extended far further south than usual. Notably, large portions of Europe and the northern United States were treated to this awe-inspiring spectacle. For observers in areas that are typically not accustomed to seeing auroras, the event was a once-in-a-lifetime opportunity to witness nature's fiery light display. In terms of its intensity, the storm was not the largest solar event recorded in recent times. Despite some outlets dubbing the event the largest since the famous 2003 solar storm, this characterization was, in fact, an exaggeration. The Mother's Day storm of 2024, which was much stronger, holds the title for the largest event in recent memory. However, the latest solar storm still stands as significant due to its ability to break a 23-year-old record for solar radiation. This was especially noteworthy for space weather scientists and professionals at the National Oceanic and Atmospheric Administration's NOAA Space Weather Prediction Center, SWPC. The storm reached a peak intensity of G4, which is classified as a severe geomagnetic storm. To put it into perspective, the G4 rating is the second highest level for a geomagnetic storm, just below the most extreme G5 level. At this intensity, the storm can have a number of impacts. Among these, solar radiation can cause temporary radio blackouts, particularly in higher latitudes. The radiation can also potentially damage satellites in orbit, disrupting communication and GPS systems, as well as other technological infrastructure. While the storm caused a great deal of attention due to the auroras and the widespread nature of the event, the specific effects on ground-based infrastructure and orbiting spacecraft were not immediately clear. At the time, it was still too early to assess the full extent of the damage, if any. The first indication that the storm was reaching its peak came at 2:38 p.m. EST on January 19th, when the storm was officially classified as a G4 level event. This first burst of intensity was followed by another period of storm activity, which reached the G4 status again at 3:23 a.m. EST on January 20th. These events confirmed the level of severity and the potential for widespread disruption, though the storm did calm somewhat between these two spikes. Scientists and space weather professionals at NOAA continued to monitor the storm's evolution closely, preparing for further disruptions. As the storm unfolded and scientists closely observed its progression, The geomagnetic field's behavior provided insight into how solar activity can influence Earth's magnetic shield. When the CME impacted Earth's magnetosphere, it caused a temporary disruption of the magnetic field lines that normally surround the planet. This disruption allowed for solar particles to enter the Earth's atmosphere and collide with gases like oxygen and nitrogen, resulting in the auroras that captivated millions around the world. While these auroras are typically visible in high-latitude regions such as northern Canada and Scandinavia, this storm allowed them to reach far lower latitudes, even extending to parts of the U.S. as far south as Illinois and northern states like New York. The auroras were not the only phenomenon that this solar storm triggered. The storm's powerful nature caused temporary radio blackouts in affected areas. These blackouts primarily impacted the high-frequency bands used by aviation and maritime communications, affecting flight safety and the coordination of ships in regions where the storm's effects were strongest. While these disruptions were temporary, they highlighted the vulnerability of global communication systems to such intense solar activity. Additionally, satellite-based systems were likely impacted by the radiation burst, although specific damage reports were still being compiled. The storm's influence also extended to GPS systems, particularly in regions affected by the most intense geomagnetic activity. These disruptions can cause errors in positioning and timing, a concern for navigation and location-based services that rely on accurate satellite data. As the solar storm's effects continued to settle down, NOAA's forecasts indicated that the auroras could still be visible across the northern tier of the United States, particularly in areas known for their high-latitude positions. The space weather experts at NOAA reassured the public that geomagnetic conditions were beginning to stabilize, but advised them to remain vigilant, as strong geomagnetic storms were still possible overnight. For anyone interested in witnessing this awe-inspiring event, tonight was likely to present another opportunity for observing the colorful lights dancing across the sky. One of the key takeaways from this event is the importance of space weather prediction and monitoring. The storm that occurred on January 19th was not a random event, but rather a part of a larger solar cycle. The Sun follows an 11-year cycle of activity, which alternates between periods of high solar activity, solar maximum, and low solar activity, solar minimum. During times of solar maximum, there are more frequent solar flares and CMEs, leading to an increased likelihood of geomagnetic storms. This solar storm was a reminder of how interconnected space weather is with our planet's technology. In today's world, we rely heavily on satellite systems, communication technologies, and GPS for everything from aviation to weather forecasting. As the frequency of solar storms increases, the need for robust space weather monitoring systems and preparedness grows. Looking forward, space weather experts are analyzing this event to improve the accuracy and reliability of their predictions. The more information scientists can gather about the behavior of solar flares and CMEs, the better they will be at forecasting the potential impacts of these events. Better prediction models can help mitigate the effects of geomagnetic storms on Earth's infrastructure and allow for more effective responses to the disruptions they cause. Additionally, efforts are underway to design technology that can withstand the intense radiation and magnetic fields generated by